I'd like to start by thanking the organizing committee for inviting me. It's a huge honor for me. I'm sure I don't deserve it. I'll try not to disappoint you. I hesitated a lot before I chose this title, this topic. It may raise many different expectations. Speech analytics for medical applications is a hot research topic nowadays. As you can see from the many different presentations, even at this conference, they were excellent. So you may be expecting something totally different. In fact, I'm only going to address two very narrow aspects of this problem, which are not so common, and in which I've been working with my PhD and master students, Joana and Francisco, and my colleagues Big Raj at CMU and Alberto Abad at my lab, and some others, but these mainly. So speech analytics for medical applications is, like I said, it's a very hot research topic nowadays, but medical applications has always been my favorite area of applications of speech technologies. Ever since I started working on this almost 40 years ago. But in those days, in spite of the fact that I was always thrilled, I was fascinated by the idea that I could apply our technologies to fields like alternative and augmentative communications for people with different disabilities, speech, hearing, mobility, vision, whatever. And now the technologies were so bad at the time. The state of the art was so poor that I think our TTS has a very robotic voice. ASR could do little more than digits at the time, but even so, our first applications were to this area because it has always been a strong motivation for me. In fact, our very first application of our TTS system with a very male voice, very robotic voice, was a system for children with cerebral palsy to help them speed up their writing and then output this robotic voice. Later on, we did ASR for automatic captioning, which was also a very important application for the deaf community, and we knew it was not that good, but when we didn't have enough confidence in the result, we just didn't show the caption. And we were one of the earliest ones to do automatic caption for TV. Then we did some other applications like multimedia books for children with dyslexia. More recently, we tried to do sign language to text language translation and vice versa. We did, of course, distance speech recognition for mobility impaired users, to recognize things in a domotic environment. One of the most recent applications were for aphasia patients to help them practice. So it was like a therapy application to help them practice to remember names of things again. It was not an application of automatic speech recognition in general. It was in the mode of keyword spotting. And in that mode, it was robust enough, even for this type of application. Then we did things for helping kids articulate better. In this case, it was also a therapy aid together with the human therapist. They were using the screen of the laptop as a mirror so that the children could see the movements of the mouth of the therapist. And also the mirror was quite important for the kids because it could show them a lot of visual rewards which they liked seeing when they got it right. A phasy application was later adapted to autistic kids, which was also a very thrilling application, especially when we tried to introduce some modules which were more directed towards improving the production and perception of prosody, of emotions, especially in autistic kids. Of course, we also try to do applications in which there was interaction with robots, namely with autistic kids. That's the robot. Oops, sorry. That's the robot of our university. At that time, with no arms, only a basket, and later on, we also did robotic dialogues for the elderly. In this case, not so elderly, because the robot was playing cards with our students, and that was something that was also very interesting to them and to us from the point of view of social robotics. To study the interactions in a group was also quite thrilling. So this was just to say that there are a number of applications of speech and language technologies to the area of medical, to the medical area, but in fact, I like claiming that virtually all speech and language technologies can find applications in e-health. But faced with the little time and the need to focus, I decided to focus on speech analytics, which, like I said, it's a hot topic of research nowadays. So why is it a hot topic? Because speech can provide a non-intrusive modality for diagnosis and for monitoring. And in fact, it has, this topic has been a frequent target in paralinguistic challenges. Ever since 2011, we started with sleepiness detection, intoxication, pathology, autism, Parkinson condition, snoring, whatever. It has really been a hot topic for research. And these challenges do not, of course, exhausted. We also have many other examples of problems of diseases that we could tackle, like with speech, like apnea, stuttering, and a number of very hard diseases like Alzheimer's, Huntington's, ALS, bipolar disease. In fact, it's not just physical health that we can help with our technologies, is also mental health. If you see, for instance, the prognosis of IBM, there are five in five, which are going to be the 5 most disruptive technologies in 5 years. 1 year ago or 2, they selected our technology. They said with AI, our words will be a window into our mental health. And it's also something quite disturbing, in fact. So, what are the goals of my talk? Given that I set the stage for all these medical applications, in particular speech analytics. The problem is that we need to build classifiers, we need training data for our classifiers, and we are always faced with the problem of insufficient training data for multimodal, non-invasive diagnosis aiding tools. So my first goal is to provide a proof of concept that we really can do, we can have an alternative to traditional way of creating databases by using large multimodal repositories as a data source. We are going to address this using off-the-shelf toolkits to perform feature extraction, filtering, classification, and then our goal will be also to compare the performance that we get in the wild data set with the performance that we get with the data recorded in perfectly controlled conditions. our second goal, it's quite different. We know that speech signals and the features derived from speech signals carry a lot of information about the speaker. We can guess their age, their gender, of course. We can guess their language, their accent. We can guess all the physical attributes like height, or whether we are in a good mood or not, or whether we have some particular disease of as we've seen also in this conference, a lot of papers on this. So health-related information is particularly sensitive. So we don't want data from a speaker to be provided to a remote server that has our classifier in the clear, without any sort of protection. And we don't want the classification, the label that the classifier attaches to this speech data, to be also available to anyone who might be eavesdropping, or even to a malicious server. So, in other words, we want to be able to do speech mining in a private way, or else do it locally. So, if we want to do it remotely, and that's our goal here, it's to explore how to do it remotely by combining neural networks and some sort of cryptography technique that that's a variant of fully homomorphic encryption. So these are my two goals. So I'll start by describing what is the baseline with which I will compare the two proof of concepts that are going to derive, the in-the-wild data and the privacy part. Okay, so this will be my control conditions baseline. Then I'll describe the work that we've done to address these two goals, and then, of course, conclusions and future work. So let's talk about our control conditions baseline. We tried to get data that could be available from a challenge. In this case, it was an inter-speech challenge and an AVEC challenge. We tried two different diseases. In fact, we tried three. We tried cold, depression, and Parkinson. But there was a limited space for the paper, and so we left out the Parkinson, also because it was a data for which we didn't have healthy controls. We only had, it was a regression task. So our two data sets for this talk will be cold and depression. The cold data set was provided in the Interspeech 2017 challenge. It's called the Upper Respiratory Tract Infection Corpus, or URTIC, provided by a university in Germany. It consists of spontaneous encrypted speech. It has only, we had three partitions. Training, development, and test, but you don't have the labels for the tests, so I'm going only to talk about results in the training and development partitions. They comprise 210 subjects each, but only 37 had a cold, so it's kind of an unbalanced set. And the chunks are up from 3 to 10 seconds. In the depression data set, the one that we got from the AVEC challenge is called the Distress Analysis Interview Corpus, or DAIC. It's an audiovisual database of clinical interviews with sessions ranging from 7 to half an hour, 7 minutes to half an hour. The training and development sets have like 106 and 34 sessions each, but only 30 of the subjects in the training sessions are classified as depressed, and 12 of the 34 in the development set. Okay, so we weren't worried about optimizing our features or our classifiers. We wanted something that could work for both in the same way, and could also work for a number of other diseases. So we chose a set of features that was designed to be quite generic for paralinguistic tasks. So we chose, chose the EGMAPS features, the extended GMAPS features. That is a set of 88 features containing information on fundamental frequency, energy, spectral, and capstral characteristics. Is one set of features per file, 88 features per file, including lots of functionals like means and deviations and things like that. The classifier, as a classifier, we also chose a very simple neural network with an architecture of 120 units in the first layer, 50 in the second layer, and of course the output layer. The first two layers share the same architecture, a fully connected layer followed by a batch normalization layer, and an activation layer with ReLUs, with rectified linear units. And the output layer is a fully connected layer with a sigmoid activation. We inserted dropout layers, of course, before the second and third fully connected layers for regularization purposes. And we normalized each feature, of course, which is the usual way. In fact, the means and the variances are computed in the training set, and then their values used in the development set. So here's the block diagram of the very common network. We didn't use a more complex network, mostly because of the size of the data. And the results for our baselines were achieved assigning different weights to samples of the positive and negative class because of the unbalanced that I mentioned when I described the two data sets. And the results are provided in terms of the most usual metric, which is unweighted average recall, or UAR. And we provided them at the segment level, not at the speaker level, because of course they will be better if we aggregate all the segments of the speaker. So for the cold baseline was 66.9%, and the depression baseline 60%. As I said, the results at the speaker level are much higher and very much in agreement with the baseline results that were provided for these two tasks at the corresponding challenges. In spite of the fact that they didn't use exactly the same features, a little bit more complex one like cover-up or something like that, and they also used a slightly more complex network in one of the cases. So this is our baseline, and you need to remember these two results to compare them later on. Let's now try to describe how we did our in-the-wild data collection. We called our corpus the In-the-Wild Speech Medical Corpus, or WSM for short. It's an audio-visual corpus that we collected from YouTube using the YouTube API and querying in the form of name of the disease, vlog. So we were interested in video blogs or vlogs, which are a very popular category that seemed quite fitted for this task. In the case of cold, we couldn't query with cold vlog because we would get lots of vlogs about the lousy weather. So we used flu vlog and got these results. We tried to come up with approximately 60 videos per data set. We did this in February 2018, and the videos published dates range from January 2007 up to February. We restricted our search to videos in English, and of course we took advantage of the automatic transcriptions provided for these videos. We don't know if some of them were manually correct. It didn't look like they were manually corrected, but they were quite acceptable. So we collected a lot of metadata for each video, not only the title, the description, the transcription, as I said, channel, playlist identifiers, date published, a thumbnail, video category, among a set of 12 predefined categories, number of views, number of thumbs up and down, and comments. Collected all that, and then we did the manual labeling of approximately 60 videos in each data set. We first labeled as vlog or non-vlog, and in spite of the fact that we queried with this keyword, not all videos were in the form of vlogs. We got some videos that were clearly PowerPoint presentations giving advice about the disease. We also labeled, is it one subject or multiple subjects in the video? Do they mention the target disease or not, claiming that they have it? Do they do this in the first person, or are they talking about someone else? And do they talk in the present tense? Like, it's no use to say, I had a cold. We want it, I have a cold, right? We got all sorts of videos. Believe it or not, we even got people claiming, I had Parkinson, but now I'm cured. So we got a lot of them. We had to exclude, of course, videos of people named Parkinson, which was not, of course, our topic, or videos of caretakers or parents, and videos of with these PowerPoint presentations. So, when we tried to do the statistics of our manually labeled videos, so you can see here numbers in terms of positive and negative class. For cold, it was quite balanced. For depression, as you can see, I've got much less depressed people than non-depressed. The vlog category was almost always there. The first person, not so much. The present tense for depression, it was very often they were talking in the past. The target topic was not always there. So if we put all this together, we see that we have to retrieve a lot of videos in order to build a significant data set of people with the disease that we want, but that was illustrative of the process. Then we tried to do something which, let's try to see if we can make automatic the process of filtering out these videos. We regarded this as a supervised classification task, which means that because our data set was so small, we just evaluated with leave one out cross-validation. We tried many different features derived from all the multimodal data that we had retrieved, transcription, audio, video, metadata. But we tried to do this with using only off-the-shelf tools, just to see if anyone can do it very, very rapidly with simple modeling paradigms. But we were interested in studying the contribution of each feature separately. So in the end, we got to compare many, many different models. So this is just a summary. For the text-derived features, we computed bag of words from the video transcription. Sentiment features for the title, the description, the transcription, and the comments using the a tool, I think it was from Stanford. We computed from the speech signal using a diarization tool, I think it was Lium Toolbox. We computed the number of different speakers. The visual features that were derived was the number of different faces, the number of scenes, and also color histograms. And the metadata features were the video category, the duration, number of views, comments, and thumbs up and down. We tried 4 different classifiers, the logistic regression and SVM with 3 different kernels. And we made predictions for is or is not vlog, first or third person, present or past tense, and is or is not about the target disease, and all of it. So the results are too many to show here, so I'm only showing the best results which were obtained with SVM with RBF kernels. You can see here shaded results that didn't prove better than what we could get by picking the majority class. For the vlog category in the cold data set, we didn't have enough negative samples, so that's why it says non-applied. That the most interesting thing here is to see that with only the bag of words in the transcription, we could do almost everything. So it was much more robust than the number of speakers, the number of faces, anything that we could say intuitively, this may make a difference. No, the bag of words did it all. And putting it all together, we could get like 80% precision. Bear in mind that we were not that much worried about recall, because YouTube is enormous. We could do lots and lots and lots of different queries. We were much worried about optimizing precision. For the depression data set, results were not that different. We also got better results from the bag of words, and altogether we got like 93% precision. The most different category to distinguish was the present past label for both of the data sets. So now we have our filtered data set, and we wanted to see how does it compare with the previous baseline that was trained with controlled data. So remember that with controlled data, we had got for the cold data set 66.9, and when we got to this in the wild data set, we got much less, 53. Okay, but for the depression, we got 60%, and then we went down to 54. So there's obviously a degradation. Of course, it may be from the recording conditions. It may be because we are getting much more variability in the effects that the disease can cause on speech. But we also have to bear in mind that if we put together all the 1-second segments that we have from one speaker, then we can come up with results that are not that different from the ones that we get with the controlled data set. So I think that what we can take from here is that we have established just a proof of concept that this is possible. We now have data sets that can be much enlarged, but because of the modular structure, we can optimize now all of the pieces that we put together. The filtering, all the modules in the filtering part, all the classifiers, all the features, we can optimize all this. It's also important to remember that the bag of words are very, very powerful, and it's one of the most simple techniques that we can use with text. And the degradation, okay, it was expected. It's something that we think we can still do. This is just the tip of the iceberg. So now let's move into our second topic. How am I doing? Still? Yeah, okay. Second topic, patient privacy. So what we want here is just another, a particular setup of what we could call machine learning as a service in the cloud, okay? In this case, we want to do mining of speech, but so the server, the classifier is somewhere in the cloud. We want any client to be able to transmit speech or speech-derived features encrypted so that the server has no access nor anyone eavesdropping. And we want the prediction that the server sends also in an encrypted form, so neither the server nor any eavesdropper can have access to it, only the speaker or the doctor who sends it, whoever, whatever. Okay, so this is a particular case of secure speech mining. There has been many techniques of doing secure machine learning in the very recent past. It's a very, very recent paradigm. In our group, together with the group of Bikshiraj, we have been recently addressing this topic with techniques called secure modular hashing. They are a variant of LSH, or locality-sensitive hashing, in which we convert feature vectors into bit sequences using band-quantized random projections. I'm not going into detail. It's quite effective. We were able to apply this both to speaker verification, to emotion recognition tasks, which are also quite interesting for call centers, for instance, whenever they cannot provide the data to a university or whatever in the clear. But of course, nowadays we have neural networks as a very common paradigm. It works pretty well, pretty much better than when there is sufficient data. So we wanted to also experiment how do neural networks combine with cryptographic techniques. And just to clarify the setup that we tried, we have speech, then all of this is done in the client side. So the client is supposed to extract features, something that I'll talk about later. Then the feature vector is encrypted with using a set of the keys that the client has, the public key in this case. The encrypted features are sent to the cloud. Then there is this encrypted neural network that provides an encrypted prediction. And the encrypted prediction is decrypted, and the only one that has access to it is the client. So this is our setup. In order to combine cryptographic techniques with neural networks, we choose a paradigm which has been known for a long time, which is fully homomorphic encryption. The idea of fully homomorphic encryption is the following. If we do an operation like an addition on the result of a sum, this will be an equal result as the sum of the two encrypted parts. The same for multiplication. If you're only able to do either additions or either multiplications, we call this partial homomorphic. If you can do both, then it's called fully homomorphic encryption. And only relatively recent are there techniques that enable us to do fully homomorphic encryption. So they are limited to additions and multiplications, And each homomorphic operation on a text, on a feature vector, for instance, increases what is called the encryption noise. So if the noise grows too large, there may be a point in which you cannot decrypt the results, so you have to control it. Normally, to reset the noise level, one can use bootstrapping, but this takes a very large computational toll. So one of the other reasons why our neural network has this particular number of layers, besides being the data limitation, is also the fact that we cannot have too many operations, otherwise we exceed what is called the noise budget, the encryption noise budget. Very recently, there's an alternative computationally lighter than fully homomorphic encryptions, which is called LHE, or leveled homomorphic encryption. It takes advantage of the fact that the user knows beforehand the number of operations that must be performed, so that eliminates the need for bootstrapping, but we have to be very careful with the choice of encryption parameters. If the encryption parameters are too large, then the operations become computationally feasible. If they are too small, then we incur into the noise gets too large, then we cannot decrypt back. So there has to be a trade-off between the noise budget and the computational complexity. So we just followed what has been already done for other contexts, for instance, image recognition, in CryptoNets and CryptoDL. To transform a normal neural network into an encrypted neural network, what we need to do is to replace all the operations by their encrypted counterparts. And because of the fully homomorphic property, we know that this will provide the same results. So this brings no problem in the fully connected layer and in the batch normalization layer. That's only additions and multiplication, no problem. But in the activation layer, the operations are nonlinear, so they must be replaced by approximations. In our case, we chose polynomials, of course. But due to the fact that this whole process is very complex, we only do inference in the predicted domain. We train that is to say, we train the data with non-encrypted speech features. Okay, that's how the network is trained. So the advantages are that one can compute a prediction over an encrypted vector for a third party without ever seeing the vector of the features or the prediction, as I said. And the owner of the model doesn't have to distribute it, which is quite good. The disadvantages is, of course, the computational complexity, which, as I said, imposes limits on the network side, and the fact that when we approximate the nonlinear operations by polynomials, they may result in less accurate models. So, as I said, we had no problems with the fully connected layers, just multiplications and additions. The batch normalization layers can also be turned into multiplications and additions, no problem. For the ReLU activation layer, we had to replace this max operation by a polynomial. In this case, we chose a Chebyshev polynomial. And for the sigmoid, we also had to use the same simple polynomial. We had to keep the degree of the polynomials also simple to approximate the sigmoid. What's important to notice here is that in order for these approximations to be effective, we have to make sure that the inputs fall within the range in which these approximations are valid. So this is also one of the purposes of the batch normalizations that we have to do. The encrypted neural network is just a regular network in which we just replace the nonlinear operations by the polynomials, but bear in mind they are still trained with clear data, okay? With some implementation details, we trained this using Keras, and we used the Microsoft Simple Encrypted Arithmetic Library, or SIL, which implements this variant of leveled homomorphic encryption called the Van Verkouteren scheme. We had to choose the encryption parameters to bear in mind this trade-off that I mentioned before. In our case, we choose a security level of corresponding to 128 bits, which means that we had to choose a polynomial modulus of 8,192 bits and a plain text modulus of 2 to the power of 30. So these powers of 2 are extremely large. This means that it took us like 750 milliseconds to encrypt a feature vector, 4.5 seconds to compute a single prediction, and less than 5 milliseconds to output to decrypt the result. However, if we choose like half of this for 4,000, then we would be down to like 1.2 seconds. So that's really a trade-off. But of course, it would result in less accurate predictions. We did this in these machines. Oops, sorry. 24 Intel processors, and we took advantage of the fact that the SIL library enables to do as long matrix multiplications in parallel. So here are the results. So up here you had the non-encrypted baseline that we had used also for in the wild data set. And here we have the encrypted one, and you can see that there's really some little degradation when, of course, we do it at the speaker level. We can get a little bit backwards. So, summarizing this part, we've done like a proof of concept of how some paralinguistic health-related tasks can be made secure by combining this fully homomorphic encryption scheme with neural networks. We've seen that there's a slight difference between encrypted neural networks and regular neural networks, which proves the validity, but there's lots of things that we can do still to improve this. Let's see then what are the main conclusions and the future work. So, if I had to summarize my talk, I would say that I started by claiming that virtually all speech and language technologies can find applications in e-health. And then I focused on diagnosis and monitoring and showed that these techniques can be a non-intrusive tool. The two points that I tried to make were that these diagnosis tools could work within the wild data. With some, it was relatively easy to mine multimodal online repositories to filter them. We obtained some slight degradation that was also expected. The second question was whether these diagnosis tools could compromise the patient privacy. when performed at a remote server. So we show that if the networks are relatively small, then the degradation is also relatively small. What are the major points that I want to leave out for the future result? In the first case, the fact that in order to prove this, we had to manually label a data set. Manual labels. How can we get around this? And in the second case, the fact that we assume that the features were computed in the client side. And that also raises problems. So what are we now doing to tackle this? In the first case, we are now working with noisy models. In other words, the models that we have built with the noisy labels that we estimated. And these models, these noisy models, when applied back to the labeled data set, have provided quite interesting results. In the case of depression, we were able to get UAR on the labeled subset that was quite high. So we were very happy with this. A comparison with the control conditions data set also yielded quite good results. So we have submitted these results to SLT workshop. In the case of the computing features on the client side, well, you all know much better than I that one of the latest trends is end-to-end encryption. So, okay, we decided to tackle this. How can we do end-to-end neural networks and combine them with fully homomorphic encryption? Well, it's not that easy because this combining convolutional neural networks with FHE imposes severe limitations on the size of the networks. Using recurrent layers, such as in LSTMs, also requires a number of operations that's too large for the current FHE networks, frameworks, so this nice budget that I mentioned, so that doesn't seem so feasible. However, if we bear in mind that nowadays, that neural networks basically work with floating point numbers, and that fully homomorphic encryption schemes work with integers. We cannot spend all our time just converting real weights into integers in a stupid way. So what we are now doing is to take advantage of the very recent work in binarized neural networks or discretized neural networks and combining them with fully homomorphic encryption. And we are getting promising results, but it's kind of a bit too early to talk about them. So with this, thank you. Dziękuję. I hope I'm saying this right.
Thank you very much for this great talk. I'll open the floor to questions. And could you guys?
So I'd like to understand a little better the cost and benefits of the encryption. For the cost, what I was had in mind. For the cost, what I had in mind was.
Yes.
Right. So I'd like to understand the cost benefit of the encryption. For the cost, what I had in mind is some kind of a multiplier of what it would cost to compute these calculations without the encryption, and how much more it would be if I did the encryption. For the benefit, I have this uneasy feeling that, say back in the day, World War II with the Enigma machine, the rule of thumb was don't let the other guys get too much encrypted data. The more data they have, the better the chances they have of breaking it. when we came out with Unix, we thought we could publish Etsy password.
Oh, yeah.
And we did for a long time, and then the bad guys figured out dictionary attacks. And so now we don't publish Etsy password. Now there's a lot of people out there who think the public key encryption stuff is safe. So there's a massive amount of encoded stuff out there. But what's I think pretty clear is that if you record all that, someday in the future we'll have quantum computers or something. And all those secrets that have been published today will be broken tomorrow. Now,
I totally share your worries.
so
Totally.
I would think that these things that you're describing, while they seem pretty safe today, if I can record this stuff, can you prove there will never be a day
No.
in which I... Right.
No. No, I think that some guy from the cryptography area would be able to discuss this with you and prove that maybe you're not correct, but I totally share your worries. I think that in what we regard as safe now, I don't know about the future. With this quantum computing and quantum cryptography, which is there, I know that it's really extremely difficult to keep up with the progress in this area. If it's difficult to keep up with the progress in speech, believe me, in cryptography, we don't even have to wait for the next conference. It's every day, anything.
So you just go to the archive.
Yes, yeah, we go to archive all the time, and every time we go, we feel that we are losing track and we cannot keep up with the progress, because it's as you said, what we had some years ago, now we don't consider safe, and this will, I don't know. I wish I could sound more optimistic. I just think that we have to keep trying to do our stuff.
So you granted the question about the future. What about the cost? So what is the cost of processing, doing a neural net in encrypted?
Well, the neural net, we try to use more layers, and even in the clear didn't help because of the limited data size. So
No,
when
that's not what I'm saying. Is if you kept the neural net encrypted,
yeah,
how much faster or slower is it than if I did all the calculations in the clear?
oh, it's much more complex, much more computational intensive.
So is
I
it
haven't
orders of
measured.
magnitude, or is it
It's orders of magnitude, yeah. But in order to be able to do to be able to work with bigger networks, we had to move to another task in which we had more data. So we are now doing language ID in order to be able to prove what happens when we have more data, and hence when it pays off using much deeper networks. Otherwise, we couldn't. Mm-hmm.
There's no such thing as a safe system.
No.
So the only thing what you can do is you have to raise the cost of bringing.
Well, so the alternative for the cost business, and even for the security, would be that imagine that I encrypt the inputs and the outputs to the net, and then all the calculations of the net are done in a vault. And then all the heavy lifting is done in the vault, so I can do it faster and safer. Yeah. All right? And then I only have to worry about the encryption going in and out of the vault, and there's probably less data to intercept there, so it probably improves the security as well.
For the time being, every operation is done with I don't know how many bits, so it's the encoding is done with.
So you're
with
saying that
stuff.
it's much more expensive to do it the way you're describing, and it's probably less secure.
Well, not less. It's more secure than having not having encryption.
No, my alternative was to do all the calculations in a vault.
Yeah.
All right. And if I trust the vault, then I'm
yeah, but trusting the vault is something that we want to avoid doing. Yeah. Regarding this question, no, very interesting one. I'll try to, with the limited data that we have, data with so 60 videos is nothing, right? Really. But believe me, these people that like to do vlogs, oh God, they talk, they talk too much. You would, it's unbelievable the amount of things they do in order to prove that they are not depressed. They go and do makeup and and hairdresser and everything. It's unbelievable. And so the videos get so long with not speech, not so much speech in the middle. So it's difficult with the data that we have because they are not talking non-stop. They are doing a number of different things. It's difficult to be able to come up with a number. We would need, but it's a very interesting question, and for sure, keep it in mind. Mm-hmm.
I have a question regarding the results of the classification. When you use the harvested data from the database, which is a great way. What do you think of an iterative process that you would,
Definitely.
Okay, so this is something you're going to do.
I mean, that's what makes sense.
Okay.
Yeah. Right now, you're working with this noisy model stuff, which is in some way leading to this iterative process.
So if you combine the
yeah.
And if you're working with vlog, did you try to combine, the video analysis for those diseases with the voice?
That was the original intention, but given the fact that we could, for the filtering, that was the original intention. But given the fact that we could get so much info from the bag of words, we gave it up. But now we have the whole data. So the data is available for any of you that wants it. So we just give the links, and if anyone with the proper expertise on getting data, bear in mind that most of the time it's just the face that you're seeing, not the posture, the gait, or something. No, not that much.
For the depression,
Yeah.
there might be lots of things.
For the depression, yes, you can get things that are. They sound so totally depressed. That it's depressing to have to label them, all of them. Yeah, because people have lots of problems, and it's not easy, not an easy task.
More questions? Did I get that right? The depression was German data,
Yes,
and you got the
English,
so you
English
tested,
YouTube. Yeah,
so you tested then on the YouTube
Yeah.
using the German training data.
but no text. The test was
Right.
just done using
Yeah,
EG maps.
yeah. Only
Yes.
acoustic data.
Only acoustic data. I mean, the results were not brilliant.
Yeah,
Yeah,
I mean, it was a tough chance.
it was just,
And given that you only had a small frame size, the results were, if you go to a larger session.
and if you optimize the features for
Sure,
that, of course. But yeah, it's true.
But could you say, let me now take those videos and use that as to increase my training data on the German house?
The mixture we haven't yet tried,
Yeah.
but the training on the noisy data and classifying that was the very good results that
Yeah.
I showed you. Yeah.
Any more questions? So the last question is, will there be coffee?
Thank you. Thank you.
Thank the speaker.
Thank you.